Hello and welcome, everybody. So today, it's my great pleasure to welcome Yong-Yeol Ahn, who is a visiting professor right now at Connection Science at MIT. That's MIT Media Lab, if I'm rightly informed. And he's also associate professor at the Center for Complex Networks and Systems Research at Indiana University in Bloomington. Waibai is a very good friend of mine, and we met the first time, I think, at Barabasi Lab. Waibai is a physicist, and as such, you may think he's not focused on cultural analytics, but that's actually not true. Waibai is interested in everything, and one of the people I know all over the world who is probably interested in most things and awesome at all those. And so basically, it is my great pleasure to welcome him today to talk a little bit about his latest work, which will deal with mobility and embedding. So we're talking about how stuff can be embedded in latent space. Mobility is actually closer related to history than we may think, because it's stuff that moves over time in space, and typically socio-cultural stuff and phenomena are determining what's happening. So this is super important and super interesting for all of us as we talk about dynamic phenomena that can be imagined as a kind of multidimensional process. So what I'd also like to add is our original idea was actually to do a lab encounter, which we may do somewhere next year. Because the Network Science Institute at Indiana University in Bloomington is a fantastic place and one of the most multidisciplinary places I actually know. It's growing like crazy, I think, still. And that's the one place where as a grad student, you can do neuroscience on a Monday, biology on a Tuesday, digital humanities on a Wednesday, and physics on a Thursday. And you're actually encouraged to do so. But I will stop my monologue and invite Waibai to give us a glimpse into his latest work. I should maybe also add, Waibai does not only do mobility and information science, he also has a strong background in network science, and also in particular in community finding. And so you can totally ask questions regarding that direction too. Waibai, thank you very much.
Yeah, thanks for having me. It's a great pleasure to be here. Nice to meet everyone. And let me share the screen. Can you see my screen?
Yes.
Yeah, so today I'll focus on the mobility, but I'll also touch upon some work we've been doing about fan fictions, if time permits at the end. Yeah, so you can reach me at yyan@iu.edu or mit.edu or on Twitter at YY. Yeah, so if you want to hear about fanfictions, you can wait until the end. And also, I would like to make this informal, so please interrupt if you have any questions. Okay, first of all, we are kind of governed by this physical space, right? We are constrained by physical space. That means we cannot put everything here. And that means we need to move around. Not so much right now, at least in US. But we must move to meet people and obtain what we want. And that means we travel through space at the level of cities, at the level of countries, and between countries. And I believe in a few weeks, you'll hear about multiple scales of mobility by Sune. Yeah. And also it happens across like regions and across countries. And what happened, as Max mentioned, like when people move, all kinds of things like travel with them. For instance, virus travel with people, as you may well be aware now. um, and also like culture and ideas and everything kind of follows mobility. And that's why human mobility has been shaping human culture, as you are familiar with it. So the question here is, what kind of factors determine human mobility? Like what makes you move from A to B? As you can guess, one important factor is physical distance. If something is far away, you're less likely to move there. And there comes like one of the fundamental kind of regularities people have been observing about mobility, and it's called gravity law of mobility. And it's very simple. So if you consider like two places, where one place has population of M1, the other one has population of M2, then by random expectation, you'll see a flow proportional to the multiplication of M1 and M2. But you need to consider the distance between these two places. And by adding a decaying function like Frij, you can get this simple form that explains the flux between two places. And what it says is like super simple. You are less likely to go somewhere farther away than somewhere close. And this is called gravity law of mobility because it resembles the formula of Newton's gravity law. But it's not only that. Max had this great idea. And what it says is that you are attracted to nice places, right? And in other words, you're more likely to go somewhere nice and awesome. In kind of spatial studies, there is something called Huff model of mobility. And what it says is you need to consider the attractiveness of the places. And usually it describes the probability that person J go to a shop I. And the idea is we need to consider the attractiveness of that shop as well as a function of distance. Yes?
Yes.
Am I unmuted? No.
Yeah, I can.
Okay, sorry. I just wanted to ask you, how do you measure attractiveness of a place? What kinds of things do you take into consideration when you kind of like measure this?
I think in practice, this can be kind of derived from actual like mobility data. So potentially attractiveness is what you want to measure, and you know distance and probabilities. Yeah. But you can consider like how many visitors they have, how many like revenue this shop makes, and so on and so on. Yeah, but these models are just way of kind of highlighting these two factors, like distance and attractiveness. And there are other models, other laws, and other factors, such as competition. Like for instance, another famous model called radiation model, take into account like how many kind of similar things are within the radius. And that explains kind of commute flow better than gravity law. But I will skip those. And regarding this theme of like attraction and distance, I would like to talk about two studies. Yeah. So the first one is about the label flow network. And again, we start from this idea, like if you're famous, you tend to move to nicer places, right? And we thought that that probably means talented people would migrate toward better companies where free food are flowing, free coffee are flowing. And the thing is, if you think about it, people should move to similar or closer firms, right? If you work at Google in Mountain View, you're very likely to move to like Facebook nearby because you don't need to move your house. And also you don't need to like learn many new skills probably because they use similar technologies and so on. And the thing is, this closeness is not just about geographic distance. If two companies require similar skills, you're more likely to move. And if two companies have similar culture, then you can fit in more easily, and that means you're more likely to move. And the consequence of that is companies tend to form these geo-industrial clusters. If you know about like U.S. geography, in Midwest around Detroit, there is a big cluster of like auto manufacturers, like Ford, and so on, and GM. And in Silicon Valley, there is a cluster of IT companies. Right? They create this ecosystem, and it's really hard to kind of, it's really easy to make a company in Silicon Valley, but it's very hard to make nice IT companies in Indiana. And the reason is that there is a strong competitive advantage that sustains these clusters. And once a cluster is formed, there is a strong knowledge spillover, and companies have a really good access to all the skilled labor inside the cluster. And also you have access to input, like all the VC firms are in Silicon Valley. So that's easy. That means it's easy to create a new company there. So because of this reason, the clusters are kind of central driver to have this competitive advantage. And in economics, many people study those clusters. But the problem is it's not so easy to study them because it's difficult to define them. Like we can conceptually know that we need to think about Silicon Valley IT clusters, but how would you kind of define the boundaries of those clusters? Or if the cluster is not so conspicuous, Texas also has like IT industry clusters around Austin, or other states may have similar clusters which are smaller. But how would you kind of define the boundaries, right? So we thought that we can probably use networks by looking at something called labor flow network. And this is a network that captures kind of how people move between companies. And we used LinkedIn's something called economic graph data, which is essentially their graph database that connect like people, skills, and companies together. And specifically, we use the job history data. So you can see like all this job history from many people on LinkedIn. And from here, you can construct labor flow network. So if a user moved from A to B, then we add one edge from A to B. And if there are like 100 people moving from A to B, then we have a weighted edge with weight of 100. And if you construct the network and look at the structure, you can see interesting clusters forming around industries. For instance, if you look at IT industries, you can see like first generation, second generation, third generation companies in Silicon Valley. And also if you look at it, they kind of deal with different world. Like the second generation, like larger focus on online services, and the most kind of hip companies tend to be more real world focused. And you can also see like how travel industries are organized, and you can see surprisingly large amount of flow between like credit card companies and airlines and hotels. So credit card companies, they work with those travel industry to make their benefits, and it is captured in the labor flow. And if you look at industries, so all the rows and columns are industry labels from LinkedIn, and you can measure how many people move between these two industries. And you can compare that to expected movement between those two, just based on the number of people in each industry. So if you look at it, you can see kind of nice cluster structure, and that indicate that it really cluster around those categories. And also you can see like geographical clustering as well. And if you just look at US, you can see like about 5 clusters cluster together.
May I just ask about these graphs? I was wondering, what are those hierarchy structures above and on the side? Maybe you could tell us a bit.
Yeah, so it's again, each state, and the rows and columns are states, and we measured the actual flow between these two states divided by expected flow, just based on the population. And once you have that numbers, we can do hierarchical clustering. And this is just a result of hierarchical clustering. Yeah.
So the rows being connected would mean they belong to a certain cluster, and then there's a hierarchy among those clusters, is that correct?
Yeah, so if you look at the topmost figure, there is a kind of West Coast and like Southwest region forming a cluster. And that means the more travel, more labor flow between those states than states in this cluster to outside other states. But you can also see that there are some flow between these clusters and the kind of Midwest cluster as well. Yeah.
It would be interesting to, it's a very classic kind of application of putting a tree on a matrix, right? But it was always interesting to look at the actual assigned hierarchies that people would give, like, you know, for example, look at football associations in comparison. Would this be the same clustering or would it be different?
Yeah.
So, right? So that is something which we have in a lot of classification. Libraries have a hierarchical subject structure, but you can also cluster them using hierarchical clustering. And there typically is a difference between the predefined worldview of the people who construct the subject categories and the actual hierarchy that emerges by doing hierarchical clustering. It's a really interesting kind of, you know, it's mind-bending if you think about it.
Yeah, and it's kind of reasonable structure. You can see like, okay, Southwest, Midwest, like North, kind of mountains, and Northeast, and then the rest in US. Yeah, yeah, maybe later I'll touch upon kind of way to compare these hierarchies using element-centric clustering. But yeah, we'll see. Yeah, so, and these are kind of useful kind of classification, clustering based on like geography, like states or industry classification. But we wanted to find like more organic these clusters, right? So we applied Lubeck method, and we kind of did like heuristic method, which is you find like communities and then keep breaking that community by iteratively applying Lubeck method. We could use more sophisticated method, but we were kind of limited to like small memory laptop in our analysis, like ironically, using the like most massive big data, but limited by like small laptops. So we used this heuristic method, and what it did is kind of break it down until like really fine-grained, like very small communities, and then we prune those communities away by looking at kind of labels, industry and geography labels. So our rationale was that community makes sense. Breaking up a big community makes sense if the resulting communities are more coherent in terms of like industry labels or geography labels. So if a bigger community is a mixture of like Austin and San Francisco, and then when you break it up, it becomes like San Francisco as a one community and Austin as another community, then it makes sense to break it. So that's the kind of basic idea. And we measure concentration of industry and location labels in each industry by looking at entropy measure. And we use that to guide like this breaking of communities. And what we found is that we can kind of compare the influence of industry labels and geography labels forming these communities. And we found that industry tend to be more important. So if you're in the, if two companies are in the same industry, you tend to move between them more than companies in the same region, which kind of makes sense. But the importance of geography varies. Like geography matters at the like really fine-grained scale, and then like kind of country level, like large scale. The industry matter most in between. And we can, because we have this cluster-based network, we can look at the structure of the whole world. And this is kind of the map. Here, every node is a cluster, like communities. And they are just organized using like force atlas algorithm. So you can see like geographic clusters like UK, Canada, Europe, all those things popping up. And then you can also see there's like a mixture of geography and industry labels. Like for instance, India up here close to like IT industries. And because India supply a lot of people in IT industries. Yeah. And you can drill it down. So you can zoom into a certain part of the network. And for instance, if you look at banking and financial services, then you can kind of see there is a cluster based on industries and then geography. So we can look at entropy reduction in each kind of level. And you can see what here bar graph shows that banking and financial services are much more influenced by industry. So you can move from like New York to LA more easily in banking industry. By contrast, if you look at retail and healthcare, those industries, they are organized based on kind of states in US. If you look at the US clusters. And entropy reduction shows that geography matter more in those industries. So it's kind of geography first, and there's still like geography-based clustering. And finally, we wanted to look at kind of the attractiveness part of it. So the question was like, does the influx of talent matters? And we define kind of talent as a high education, like college degree. And we looked at kind of growth in college degree influx versus market cap growth of the companies. And if you look at kind of company level market cap growth versus like influx, you see some correlation, but it's really weak. It's very noisy. If you look at geography, it doesn't really have correlation. Industry level, a little bit better, but not so much. But if you look at kind of these clusters, it shows the kind of strongest correlation between influx of people and growth of those industries. And in other words, this network method kind of captured the most organic and coherent unit of analysis. And we can look at each cluster in terms of like influx of talent versus how they kind of grew. And if you look at just the region, we see like Seattle area, San Francisco area, Dallas area, they are kind of growing industries in terms of like flux and then how fast it grows. If you look at industry, you can see computer software, real estate, and so on. But these two doesn't show the full picture because they are looking at one dimension only. It's important to get them together based on this cluster level to identify like what's going on. So for instance, real estate is growing, but it's in the great Los Angeles area. And at the time, there was like massive flux of like IT companies buying offices in Los Angeles areas. And you can also identify like computer software is growing, but it's specifically growing in San Francisco and Seattle area, which makes sense. So the point here is we need to look at both, like industry, which industry, as well as like which place. They both matters. Any questions?
There are some questions in the chat. They're going back, but maybe I can read the one to you. So is there like such a thing like an event horizon when it comes to attractiveness of places? When there are forces to keep you in place stronger than those that drive one to move away. So maybe Jan, you can specify a little bit what you mean with this. Does that make sense?
Yeah, I can probably elaborate. This question comes from, well, astronomy, and the event horizon is the point of no return when it comes to approaching the black holes, but it also happens in of course in automation systems when systems go off accidentally and there is no way to return and stabilize the system. So when it comes to workflow, is there such a thing that places are basically black holes and they attract people, and maybe someone who wants not to appear exactly in Microsoft, let's say, but they reach this horizon line and they end up in Google, let's say, just because the forces are stronger.
Yeah, I think that's a very interesting question. I think what prevents like industry cluster black hole is like limitation of physical spaces and building code. Like San Francisco has a really strict building code, so you cannot make a lot of housings in the Valley area, and that means you cannot make these super high rises. And that means that then still people are kind of limited. Well, yeah, but I mean, Silicon Valley, for instance, is very similar to not maybe black hole, but maybe neutron star, because it attracts like everything so much. I mean, you need to pay like $2 million to buy like really crappy house.
But can I comment one thing? Like,
yes.
but I think this is there is two things that I come to my mind when you said this. One is like has been problems of non-compete of these companies. Actually, that there were like kind of an agreement to not compete for and I thought that they had a fine between also, that this big tech, they were not competing between the employees. But actually, I think that it will be very nice, like now that you study the clusters, I have a few friends that they work in this big tech. One was in Facebook and recently got the agreement to go remote. And he actually moved to North Carolina and bought a house. Because like he was in Silicon Valley and of course, I don't know what they had there, but I think it was pretty small what I saw the pictures on the house that North Carolina got. And these people is not coming back because he got like green light to go full remote, and he's moving to a nice house and he's not coming to the Valley.
Yeah, I mean, coronavirus turned black hole into a white hole. Yeah. I mean, that like really highlight kind of how kind of absurd the living price is, right? Because there is no restriction to work at the office, it just doesn't make sense to live there. And that kind of ironically shows how strong the pull is toward these clusters. And you pay like $5,000 rent per month's rent to just work in like these nice companies. But now you can live with like, I don't know, $1,000 rent in like Texas while working remotely.
I met people who moved from Texas to Germany to work remotely to not be there anymore. That is an interesting question, is like, how does the sprawl actually, like you have San Francisco, which is always the example, right? But there is also Phoenix, Arizona, Dallas, Fort Worth, Shenzhen that grow like 5 to 25% per year. And then at some point you sit out in the sprawl and there is like, there's people, I had students who came in from Montana and said like, I'm so happy I'm now in an urban situation. It was like, okay, get a flight ticket to New York, please. There's no urban, right? So you could literally like walk for 3 hours and there was nothing, you still didn't hit the supermarket. And so the question is that, that is, I think, a question in the long term is like, what is the actual shape of space other than like these, we're still talking black holes and neutron stars, but the question is, what's the Hubble deep field of the whole thing? So, yeah. So, is there? There's right, Mark.
I can, yeah. Oh, it's just a comment that on the attractor that it sounds like awfully close to the cultural evolution is called like cultural attraction. I'm not acquainted with it enough to explain it that well, but just the idea that if there's like transformations happening, then biases and everything, like there's like you said, this distance, for example, or like how nice the place is, the biases that force these transformations toward this total specific location. So the transformation would be mobility in this case, and so basically this industry locations would be cultural attractors in this terminological framework. So I just saw like connection. I'm not sure if it's like fully valid, but yeah.
Yeah.
So that's a general, thank you very much for that question, because I think it's in general a really interesting one to think about. That, if you do data science and you or information science, you measure stuff and then you name it. While in semiotics, you sort of theorize about things which then have names. And so in both areas, you have this issue like, okay, how do you validate sort of your naming in essence, right? And so this is why this community finding in the background of this particular work is so interesting, because I remember we had a phone call about this at YY where we talked about, I had an issue where I had a clustered matrix, which you had these nice little rectangles, so nice clusters, but there was also stuff going on the diagonal, off the diagonal. And
Yep.
exactly that shape, that's the interesting one, where you cannot, obviously you cannot draw a line around it, so you don't have a name for it. And so that is exactly the point, is like, how can you break with the categorical conventions of traditional humanities in order to extend humanities in a sense? So how did you make any progress since that phone call? It was a while ago. After the clusters, so how do we deal with that?
Well, I mean, in a way, this whole community detection is kind of breaking away from this kind of industry and geography classification. And a lot of diagonal elements happens because it's not just industry, it's not just region. Mm-hmm. It's both are in play, as well as kind of in between. Yeah. I mean, it's also kind of related to edge-based, link-based thinking. Mm-hmm. Instead of thinking about like certain industry, maybe you can think of like industry pairs and their interactions. And actually in neuroscience at IU, there's something called edge functional connectivity, which has been published in Nature Neuroscience and PNAS last month. Mm-hmm. And the idea is, let's look at the edges in brain connectome, like functional connectome. And let's think about like those in-between edges and how they vary temporally, and focusing on that. So yeah, it's interesting to see those things.
It's also funny to think that they took till 2020 to have that idea, right?
Yeah, actually, like last year, there was a neuroscience workshop, and I talk about like link communities, and I was mentioning, oh, there is this study that applied link clustering to connectome data, and then Olaf and other neuroscientists here approached me after the talk, and there's this only one study, exactly one study who did that, and there was nothing else applying the same idea. And apparently that talk sparked them to pursue the idea. So yeah.
Thank you very much.
Anyway, yeah.
That's the reason we invite you. Yes, thank you very much. Continue.
Yeah, so also you can look at like skills, like what are the skills that are kind of popping up in most kind of growing micro industries versus like decreasing, like declining industries. And you can see a lot of oil, gas. This is from like what was it called? Like new techniques to mine oil from oil sand, as well as kind of fracking and boom. There was this boom about like oil and gas, and you can see that. And like declining skills are like teaching, public speaking, like leadership, Microsoft Office. Yeah, you can kind of see this different polarization of skills and things like that. And interesting thing is like declining skills tend to be really kind of vague and general. And even though similar skill, similar types of skill, if the name is more specific, it tends to appear in the kind of growing skills. Like leadership will be declining skill, but a cross-functional team leadership will be important skill. So it's also about like how users put their skills into their profile as well, in a way. Okay, as a summary for the first part, so we use something called label flow network, and we define these clusters using network community detection, and that allows us to kind of map it and see how they are interconnected with each other and how they are related to like growth of industries. And this is our team. And it was really interesting experience working with this massive data set and with a company. Yeah, so going to the second study about mobility embedding. So again, the idea starts from the fact that the closeness between places is not just about geographic distance, right? And the thing is, now we have capacity to fly across continents. And like throughout the history, humans have been like kind of gradually overcoming this geographical constraint. Like if you look at like, for instance, diffusion of metallurgy, you see it's spreading just based on like this spatial dimension. And on the right, you have the spreading of like Black Death. And now you see a little bit more kind of sea route. And you can travel through sea a little bit. If you look at like SARS map, how SARS spread across countries, it's all over the place because it's all connected to air travels. And if you, for instance, if you're living in Australia and you're moving, if you compare like Indonesia, which is right next to Australia, versus UK, if you are from Australia, you're more likely to move to UK, although it's like way far away. If you're from South Korea, you're much more likely to move to US to study or to work than moving to North Korea, right? So what I want to say is physical distance matter, but now cultural and other factors play much more important role in constraining human mobility. And that leads to the question like how can we kind of define and measure distance between places? You can measure geographical distance, right? But that doesn't like mean a lot right now because of air travel and because of the flow of people across countries. So how can we kind of define measures of distance? And an interesting idea here is something called effective distance. And in terms of like disease spreading, you can think of effective distance in terms of like how well these places are connected through travels. So on the left, if you look at geographic distance versus when the disease arrived at airport or country, you don't see a lot of correlation. But on the right, if you construct a network based on effective distance, which is roughly 1/, kind of flux of people. So the more people travel between these two airports are closer. And if you do that, you can see like really nice correlation between effective distance and how long it takes to arrive, the disease to arrive at the place. So it's much more useful measure of distance in the context of epidemic spreading. So, yes.
just so I understand correctly, so here you have geographic distance and network distance, but does the effective distance combine both of them, or is that a separate term?
In a way, it combined both because it measured the flux, right? Flux between places. And as you know, like flux is a function of distance. But it also captures like how culturally similar they are. For instance, Australia and UK may have a lot of flights given the distance.
So there is an easy additional way to understand it is, you know, these concentric plots. If you look at the dot in the center, that's like an imaginary place where a disease starts, like Wuhan for coronavirus. In this case, this is SARS, something else. But so imagine that is like the starting airport in Wuhan. And then like the first links go to all the airports that you can directly reach from Wuhan, which obviously there is some Frankfurt is somewhere, right? And then there is the hop 2 airports. There are 2 hops from Wuhan that you connect to the airport where there's the most flux going on. And so it's both at the same time, sort of the steps away from the original airport, and then you give a weight to the link, which is, as Wawa says, the flux. And in this particular case, what's really interesting, that there's a famous video where you can see like the disease moving all over the place, as we have seen in coronavirus. There was lots of animations for that too. It looks quite chaotic. And like the idea in the past was for every airport, for every city, you would have a little computer that calculates what all the families do. And what this paper does is reduces the model to a concentric wave on that circular plot. And then basically you have like, you know, 1 or 2 variables in a very simple formula. And so there's this paper is by Dirk Helbing and Dirk Brockmans. It's the famous Dirk and Dirk paper, which basically reduced sort of the 30 people, using massive amounts of energy, glamorous model of Alessandro Vespignani and many co-authors to something 2 people can do basically on a pocket calculator. And so, but it only works at the beginning of the disease. And I think that it's a really interesting, powerful thing that 2 people can still come up with. That's the other message of the paper. I can still come up with something that's globally relevant and makes computation way cheaper, which is sort of funny. Yeah.
Yeah. So you kind of recover kind of hidden like geometry within like spreading dynamics. So yeah. So the idea is like in Black Death, for instance, you can see kind of wave front moving across Europe. Can we recover similar kind of spatial pattern out of this messy world where everything is connected? And we can do because everything is connected, but the connection gives us the information, the hidden network structure. Not hidden network structure, the hidden geometry structure. Okay, so our question is like, can we learn the space, kind of embedding space where you can imagine like vector space, high-dimensional vector space, where every location is a vector, where this effectively capture the distance between the places, like in the case of the disease spreading. So that was the idea, and we use several data sets, including scientific mobility. And for scientific mobility, we use Web of Science, and we extracted all the affiliation of the authors, and we tracked from 2008 to 2019. So if someone moves between these institutions, we construct these trajectories, and we use that trajectory to kind of construct the flux between institutions, as well as kind of sequence of transitions. And if you look at geographic distance, it matters. If you look at geographic distance versus flux divided by the mass term, the population term, it still shows a fair bit of correlation. which makes sense. And we can also do like prediction of flux using the gravity law. So we can do prediction versus the actual flux, and it make a decent prediction. But our idea was that maybe we can try so-called the word-to-back method on this trajectory data set. So word-to-back is a kind of neural network method where you just put sentences into it, and then you get vector representation of word out of it. And how it works is you try to learn the vector representation of each word that is really good at predicting nearby words vector representation. And by just doing this simple optimization, you can obtain these vectors. And an interesting thing about word-to-back is that the geometry encodes kind of semantic relationships like gender or country versus capital relationships and so on. So we were curious what will happen if we apply that. So based on this trajectory of each author, we get a sentence of institutions. And we can just directly feed that sentences into word-to-back by considering each institution as a word. And if you do that, you can actually do much better. So if you measure cosine distance, which is not a real distance measure, it shows much better correlation with the actual flux. And they can do much better prediction than geographic distance. In other words, once you get the embedding, like vectors of each institutions, then you can measure distance in the embedding space. And that is much more useful than geographic distance. And we checked other data set as well, like US flight itineraries and like hotel reservation in South Korea. And in both cases, the embedding shows much better kind of fit to the model. And once yes.
So you're basically suggesting embed everything. That's like the consequence of this. Is that true?
Well, that's what I've been doing recently quite a lot. Like let's embed and see. And I think it works pretty nicely. And we are also working on kind of theoretical base of this. Mm-hmm. And actually in word-to-back, objective function resembles gravity law formula, actually. Mm-hmm. So there is a kind of theoretical reason why this happens. Yeah.
Oh, so this is similar to the KL divergence also being heavily used in neural networks. So we have to be super careful to not have a circular kind of argument going on. Is that true? Or?
Yeah, it can be a little bit circular because embedding aim to find the vector that satisfies this objective function, and objective function kind of resemble the gravity law. Mm-hmm. So it makes sense. It kind of makes sense that it finds vectors that satisfy gravity law better. Mm-hmm. But I think that's a nice thing, actually.
Okay.
Yeah, because we can, once you embed the physical space into the embedding space, then we can use that as a way to kind of capture all these social cultural factors into account.
Maybe you could just briefly say again exactly how you embed it, because you showed it with words before, so that's quite easy to understand that similar words go together. But in here you have, like you said, hotels or flight trajectories. I would imagine it's not just the title of the, like the name of the hotel, or is it?
It's the name of the hotels.
It's just the name?
Yeah, it's the ID of the hotels.
Okay.
So for each ID of the hotel, so you can think of it as a unique name. and each unique name of the hotel is a word. And there's a sequence of hotels based on one person's trajectory. And we consider that as a sentence. So in word-to-vec applications, it's just about like finding sequence of unique items and consider them as a sentence and unique items as words. And you can apply word-to-vec in so many different things by just conceptualizing this that way.
So whatever is a sequence.
Yeah, whatever is sequence with unique items.
So you're just looking at similar sequences then, right? Is that what would you then say that you were saying that it works better looking at the embeddings rather than the geographical actual location? So would it mean that it's easier to tell which hotels belong together based on the sequence of how people took trips to those hotels rather than where they actually are?
Yeah, in a way, yeah. So if two hotels are very similar in terms of like their style and their customers and their properties, then even though they may be a little bit far away, people tend to visit them in sequence. Yeah.
So Hilton should be a random walk. Nice. Mar, you also.
Yeah. And then basically, it's very interesting, this approach. Means you basically, whatever you can sequence, you use it as a phrase in a way, and then word2vec will find the kind of like
in another study we use citation network and we generate like citation kind of sequence. So you keep following the citation of a paper, and then we use that to learn embedding of journals. And once you get embedding of journals, you can do all kinds of crazy computation, like, okay, this conference or this journal minus physics plus biology, what will you get? You can do those kind of crazy stuff. So yeah, it's really powerful because any sequence data can be turned into embedding.
I was just wondering, so I work with movies and I look how films travel around the world. And with people, it's quite easy because it's hard to be at one place in one time. Like one person would go to this hotel and then that one. But when you release a film theatrically, for instance, then a film might be in many, many cinemas all at once. So I was wondering, would this technique also work where events happen simultaneously in different places?
Yeah, good question. I don't have very kind of straightforward idea right now, but there are also other embedding method called like star space by Facebook, which is even more general. Like you don't even need any sequence. You just need kind of similarity measure between anything, between any entities. So that's kind of, yes.
I got an idea. So the films are in many different places, just like words are in many different sentences. So your sentences should be the cinemas, right? That would make much more sense. And then you can add some sizzle by replacing the movies with, say, the actors that are in the movie or something like that. Or so you get more sense-making similarity structure because every movie is only once at a cinema, but there may be a recurrence of like Warner Brothers movies versus DreamWorks movies or whatever, right? So I think there's lots of stuff one can play with in terms of coarse graining and fine graining the whole thing, and if that makes sense.
Yeah, I think that's an interesting idea. And one thing I want to also note that is word2vec, it's the best to have a nice sequence, meaningful sequence. But even if you have a set, you can still run word2vec because you can consider set as a kind of window, like horizon that you look at. So given a set for each word, you try to predict all the other words in the same set. Then you can learn the embedding. And you can also do something called like doc2back, which is an extension of word2back method to documents. So the idea is you can learn the vector representation of set of words by just trying to predict all the word vectors using this document vector. Yeah. So there are like lots of variants of embedding method. And yeah, embedding method seems to be quite powerful in many applications. Yeah, so embedding distance works. And also it allows us to draw nice maps because of this nice method like UMap. And it's kind of funny in a way. Sometimes we do graph embedding by generating like random walk sequences, right? So you start from network, you generate sequence and learn the embedding like vectors. And then what UMap does is a kind of construct the graph and then try to put that graph into the space, two-dimensional space. So you go from like graph to vectors and graph to vectors. You're muted.
I said it's like food in the ocean.
Yeah, so you can see a nice country level structure. And it's actually, this is what you can see topologically. If you have a globe and if you look from like a North Pole, it's kind of countries are arranged in the same way. And an interesting part can be like Quebec. Quebec is actually closer to France than rest of the Canada in terms of like scientific mobility. And it kind of makes sense because of language, right? And the benefit compared with like a network method is that if you visualize networks, you cannot see much. And part of the reason is that network, the hubs in the network really make it hard to kind of visualize the network. The hubs are connected to so many things and it kind of add a lot of noise. But in embedding space, like everything is the same vector, same dimensional vector. It's somehow much easier to visualize than networks. And especially in like scientific mobility, because there are so many institutions with a lot of mobility, a lot of researchers, like top universities. It's really hard to visualize them. And you can see like interesting like regional zoom ins. Like if you zoom into like Asia and Middle East, you can see kind of from Middle East to South Asia kind of spectrum. But also you can see the influence of like religions. Like Malaysia, for instance, is closer to Middle East in terms of mobility. And if you look at South America, you can see cluster based on like language. Brazil, Portugal, they are closer together. And then other Spanish-speaking countries are closer together. And you can zoom in, yes.
I have a question regarding, so this UMap stuff, it always looks so awesome, but then you hit, if you look very closely, you hit these places that are sort of wormholes, right? Like there's some things, like the really interesting several places at the same time, or is it a place and you don't really see where it, you know, the connection. So how do we deal with this?
I think the most basic thing is you need to be keenly aware that can happen. Many people are not aware. So be very careful interpreting UMap or T-SNE visualizations. And what's important is whatever you observe in the map visualization, you need to confirm with the original vectors. So what I said here, like Quebec is closer to France, Malaysia is closer to Middle East. All those things are confirmed by calculating cosine distance in the original vector space. I think that's very important. Like whatever you can see from the map, you need to confirm with the actual numerical measurement. And just use UMAP as a kind of visual guide to explore.
Nice. So you could map the exceptions and mark them out, and that's probably the really interesting stuff, right?
Yeah, yeah.
All the silos in the university, but we would never find CUDAN because we're spread out through that. So we're in nowhere space. So
yeah, that's actually an interesting idea. Kind of supplying UMAP or any other visualization by measuring how kind of inaccurate a certain region is.
Mm-hmm.
And if you can overlay that on the UMAP, that would be quite useful. Those wormholes, essentially, or the wormholes.
Let's write a paper and dedicate it to Fritz Zwicky. I can. Let's write a paper and dedicate it to Fritz Zwicky, who was like the astronomer who found stuff like this. Okay, thank you.
Yeah. So you can zoom in wherever you want. Like if you look at Boston, you can see UMass system kind of isolated, and all the prestigious universities are kind of forming their own cluster, and so on. Yeah. So you can do all kinds of interesting overlays. For instance, you can look at language family and you see these clusters. And we can also zoom out by defining a vector for country or region by averaging all the vectors belong to that country. Then we have a single vector per country, then we can operate on the country level. And once you do that, we can get this metrics connecting countries. And we also did like simple hierarchical clustering here. And then we look at language family, and region, like continents. And what we did here is that the clustering result, which is just based on the vector, embedding vectors, and we compare that clustering result with those classifications, like region, language family, and language. And what we use is something called element-centric clustering that we proposed several years ago, which is you have two clusterings, right? And then it allows us to compare the clusterings together. So clustering A group like Finland and Denmark together, clustering B group Finland with like Sweden together, then how different the clustering is at the level of elements. So in other words, you can imagine from the perspective of a single country, how my local neighborhood different from this clustering to that clustering. And we can put a number to each of the elements. That's how element clustering works. A nice property of that is we have a tuning parameter called scaling parameter. And when we compare like two hierarchies, we can kind of tell this method to focus on higher level structure or lower level structure. So that's a tuning parameter. So it's a kind of horizon, your information horizon. So if R is very small, it looks at like top level structure. You only care about like how roughly it cluster structures. And R is higher. If R is higher, then we focus on like really fine-grained structure. So for instance, at large R, we are comparing the language, the comparison with the language produced the largest value, largest similarity. That means if you cut the hierarchical tree at the close to the bottom, then it resembles the language clusters. If you cut the hierarchical tree near the top and use these large clusters, it resembles the region classification. So this map kind of tells us like what are the kind of organizing principle across level regarding the embedding space. So, I mean, as you can expect, there's a strong correlation with the language and then language family, and then like this large geographical regions. Any questions?
It's let me just say it's fascinating. So this, can you point to the paper where you published this, because I think it's actually really
yeah, so it's a scientific report. I think the title is Element Centric something, I forgot. Yeah, it's by Alex Gates.
okay, yeah.
And several other authors.
Yeah.
Yeah, and we have a package called Clusim, CLUSIM, on GitHub. And this package implements our method, the element-centric comparison measure, as well as all kinds of other existing clustering measures. So if you just use it, you can compare two clustering together.
No.
Yeah.
That's a recommendation for everybody who wants to get deeper into clustering. Because clustering, the problem with clustering is you can cluster something and then you don't know what it means, right? And so an easy weapon to actually circumvent that problem is to just compare different clusters, different clusterings. Typically, as I said before, there is some natural clustering, like, you know, people put books into different departments of the library, or we have different affiliations within the university. But in essence, then you find some other things that's based on the links. And the question is always, how do you compare them, right? And up until now, you get away with visually just publishing matrices, like in this PNAS landscape paper we had with Yong-Yeol Ahn, actually is Weiwei's PhD advisor, which is quite funny. And so we published matrices where just visually we got away with saying, you know, you see similar cluster structure, but it's different in detail. Like, once such comparison methods that are more structured are around for a couple of years, this will go away, I'm pretty sure. And then people will actually ask for a proper kind of analysis and put some rigorous argument behind it, in essence.
Yeah, so this
package
is
for hierarchical, but probably not only. I see here different clustering.
Yeah, so the nice thing about this method is that it can compare any kind of clustering, whether it's overlapping or not, whether it's hierarchical or not, it doesn't matter. We can do everything. We turn every clustering into kind of bipartite graph between clusters and elements. And we construct element level graph out of that based on like diffusion process. So in other words, we are asking, okay, I'm node number 1 or element number 1. It doesn't even have to be network clustering. It can be at any clustering. Node number 1, from my perspective, how close is number 3? I'm node 5, how close node 7? Like, for instance, in the second case, node 7 is indirectly connected through like overlapping clustering through 6. In this case, number 7 is connected through this hierarchical clustering. And then once you construct this graph, we can compare these two matrices and then obtain a measure. And we can have a tuning parameter. And probably this example would be kind of interesting. So this is a college social network, Facebook social network. And we compare the clustering found through modularity method with labels like year or dorm or major. And here you can see that the first year label coincide with the network community really well. So at the first year, you form the link between basically among the freshmen. And as you move along, like second, third, it become like weaker. While like major and dorm play more important role gradually. So in other words, it kind of tell us like what are the organizing principle of these clusterings by comparing with the labels. And also you can measure something called frustration. So you run clustering many times on the same data set. And for each element, you can measure how unsure the clustering algorithm is about this node. And that may indicate that this node may play kind of connector between clusters. And that's why it's hard to classify. And you can have like high error but low frustration, which means clustering algorithm constantly wrong, but it's very consistent. Or you can have a low error but high frustration, which means it doesn't get wrong very often, but it's not sure as much. So you can kind of have an extra dimension to assess clustering, like how frustrated it is.
So I have a stupid question, maybe. So you construct your little weighted graphs, which allow you to compare basically using a random walk locally, right? So,
yeah.
So you basically get around the no free lunch theorem by taking two things that sort of assume lunch costs this or that. And then instead of like trying out all different things, you just compare locally. So that's a really interesting. So maybe I have to explain to the rest. So no free lunch theorem says no clustering algorithm can be optimal in all situations. So the best thing you can do is doing random walks, which is obviously ridiculous. If you have a large system, you cannot afford doing random walks everywhere. But what you do is you basically take two assumptions, which is your two clusterings, and then you do the random walk locally, and then like you're doing better than each one of the clusters. That's basically the premise of the whole paper, isn't it?
Not so sure. I should think about it.
But it's super interesting. Okay. Nice.
Yeah. I think it's very useful method personally, because it puts numbers to every element. Like you can ask questions about elements. Okay, for this node, this element's perspective, how similar are these two clusterings? Am I kind of consistently classified across these clusterings or not? Yeah. And you can kind of probe like organizing principles of the clustering by comparing with the labels, other existing classification. Okay, yeah, so be sure to check out the open source package. We also have a publication about that package as well. Yeah, and other interesting thing is, again, like semantic accesses that you can probe in the space. So what we developed a couple of years ago was that it's like a super simple idea. You grab a set of words, like kind of positive, and another set of words as a negative, and then you create a vector from negative to positive, and you project any other vectors on this axis. And that score, the cosine similarity, tell us like which side is skewed. So you can have a sentiment analysis using that, with an excellent accuracy, and you can do all kinds of weird stuff. And the same idea was published by James Evans last year, and the title was Geometry of Culture in ASR. Pretty nice paper, you can check it out. And they looked at like, okay, in terms of gender dimension, or in terms of one dimension like gender, how the sports kind of are located in the space, or things like music genres, like in terms of like racial space, like how they are located in those cultural space. It's a very cool paper. Anyway, so we can do the same thing. We define two axes. One is East Coast of US to West Coast of US, Massachusetts to California, and then prestige, like highly ranked universities versus low ranked universities. And this is kind of map you can see. And the interesting thing is, if we use few like institution at the top as a kind of one end of the axis, and the bottom like 5 at the other end of the axis, and line every university up, it has a pretty high correlation with actual like ranking, university rankings. And if you compare with Times ranking, the correlation coefficient is about 0.8. So it's really well correlated. So in other words, this embedding space somehow capture a dimension in the space that's about prestige. Does it make sense?
Yes, it does. How many dimensions does the space have? That's a good question too, right? Isn't it?
Yeah, I think it's fairly robust. I think we use probably 300 dimension, but I think, yeah, it doesn't really matter.
And is that, one could ask the questions like, to how many dimensions do really matter, right? Like, do you read 300, or do you need 20? Do you need 15?
Yeah, we have a paper on the archive about what will be the optimal dimension of network embedding.
Okay.
And usually you need much less than what people usually use. But the point, an interesting point about embedding dimension is that increasing the number of dimension doesn't seem to hurt much. Like in machine learning, there is something called bias variance trade-off. So as you increase the number of parameters, your bias decrease, your model become complex, your model become much more accurate, but you lose the generalizability and you overfit, right? There's this nice trade-off, and you want to find the optimal parameter. But in embedding method, these trade-offs seem to be kind of really asymmetric. So if you have a too few dimension, it doesn't really work well. But having too many dimensions doesn't really hurt much. So it's better to err on the side of more dimensions, actually.
So you can be an artist student and still worry about restaurants while being an artist student. Okay, thank you. Nice.
Yeah. And an interesting implication of that is we can kind of infer prestige where there is no ranking. Like government institutions or teaching college, we can still infer that using that dimension in the space. And it produced reasonable result. Like Wellesley is famous, like a women's college, liberal art college, which is near the top. And it's fairly robust given like how many data points you use. And other interesting finding we had is kind of norm of the vector has some interesting meaning, like the length of the vector. And the idea is the large vectors are kind of more attractive because the objective function multiply these two vectors together, calculating the inner product or cosine similarity, and then use that as a kind of probability function. So if you have a large vector, you're more likely to attract, you're more likely to appear in the sentences. But interesting kind of side effect is that if your length of the vector is too large, then you cannot appear much in other contexts, because being strong in one direction means that you're weak in other directions. So what happened is this kind of boomerang shape pattern. So number of researchers is highly correlated with number of like publishing researchers is highly correlated with prestige. So as you go, more researchers tend to become more prestigious. And at the beginning, it increased. So as prestige increase, the size of the vector increase, because you're more likely to appear in the sentences. Okay, but at some point, after some point, it starts to decrease because you're appearing too much everywhere.
Can you explain this in another way?
Maybe astronomy kind of analogy may be useful. So the norm of the vector is kind of the mass, kind of attractive force. Mm-hmm. Okay. So the bigger the norm is, you're more attractive. But if you are too attractive, well, I guess it breaks down. But if you're too attractive, you can just be at the center, and you still, it's enough. I mean, there is a trade-off between kind of having large vector and having a lot of attractive force versus the need to appear in many places in different contexts. So if you need to appear in many different contexts, it pulls the length of the vector back, because having a large vector in one direction prevents you from appearing in other directions.
So can you then say that institutions that are prestigious are more focused in certain areas?
Until some point, but after that, it's too universal, too ubiquitous to have a large norm. Like Harvard, it appears everywhere. It appears so frequently in the trajectory. It cannot have it cannot have large vector, because it will prevent their probability of appearing in all kinds of other contexts. Yeah. So if university appear in only one context, then it will have a large norm. And actually, kind of universities that have more kind of specific, well, I think it's a little bit hard to say. We are still trying to understand like what's going on, but that's kind of rough idea. This
Maybe you could just repeat exactly what the vector size measures?
Literally, you have a vector, like say 1,2, then it's the distance between the origin to the 1,2. That's a Euclidean distance. Yeah. And this has a nice correlation with prestige, and it's universal across all countries. Like whatever country you look at, you have a boomerang with the most prestigious on the right. Although some countries doesn't have the right end of the boomerang. They only have this increasing part of the curve.
Would it make sense to take a look where the Egyptian scientists go when they have a certain level of impact? Is Cambridge the right end of Cairo?
Yeah, that would be interesting. I mean, we have several Egyptian scientists here at IU as well. Yeah.
Okay, interesting.
Yeah, globally it has very clear boomerang shape, and a country like US, China tend to have more of the kind of decreasing part of the curve. Yeah, so this is kind of the curve we can look at. Yeah. All right, so in this study, we basically apply word-to-back to trajectory of like human mobility, and show that once you get the embedding, it better explain kind of flux between locations. And that means we can kind of use that space to study all kinds of things. Like, for instance, we can probe what are the organizing principles of those clusters, and what impact the mobility. Is it the language? Is it like the geographical locations? Or if you can measure other factors, then we can study them. Yeah, and in terms of like science of science literature, I think this is also interesting that this embedding space capture like prestige as well as kind of prestige in interesting ways in terms of like the norm of the vector, in terms of like finding accesses in the space. Yeah, so these are the people in the team. And do you have any question about this study?
There's no questions in the chat, but maybe there's questions in the audience.
I have a short one, if I may.
Sure.
Yeah.
Thank you very much for the presentation. I'm kind of still having in mind a question about mobility usage. So if you use mobility data, it obviously have a temporal dimension. So, and that is how we may require some robustness analysis of the similarity. So if you take 1 year period of mobility, you may end up with 1 similarity measures. If you take 2 years, so did you actually perform that robustness, and what were your findings in this way?
Yeah, our robustness check was mainly based on different data sets, not along like temporal range. For scientific mobility, we have about 10 years, and we thought that is kind of reasonable time frame, given how frequently people move in academia, like 4 or 5 years in the PhD, and then several years postdoc potentially. Or if you have become a professor, you tend to, I mean, the 10 years is kind of reasonable time scale, in our opinion. The hotel data set has much shorter time scale, as well as US itineraries. Itineraries happens within a day or two. So it's very different time scale, but everything still shows the consistent pattern.
Yeah, but it is fixed, right? For all the results, the time scale is fixed. Okay, thank you.
Yeah, yeah.
Is the median itinerary length 2, or how short is it?
What?
The itinerary length is typically very short, right?
Yeah,
So,
I think we discarded like only one hop. So it should be at least 2 hops. And I guess the median should be 2 hops.
Okay.
Yeah.
So the question is, you would not recommend doing this when you have only source and target, which in art, this is typically what you get.
I think you can try, but I think the richer the trajectory is, the better.
Okay.
Yeah.
Thank you. Any other questions? If not, we got some fan fiction.
Okay, yeah. So I just copy pasted the slides from my talk at NSI. So this is a wonderful artwork by Bill McConkie. And as you can see, it's kind of wild. Yeah, how many do you recognize? The pregnant Kirk. Yeah. Anyway, so fan fiction. Anyone familiar with fan fiction culture?
No, nobody tries. Nobody can admit that they're not familiar. No, I'm much.
Oh, right. I should not ask.
No, you should know. There are lots of people I think are very familiar, but I'm not.
Yeah. So it's kind of wild world of kind of participatory creation. Yeah, where people create kind of their own creations based on certain canon, right? So you have Star Trek, and people write random creative stories using the characters and settings of that canon. So that's fan fiction, and there are a lot of online communities, and it's wild. Very frequently, the male characters get pregnant with another male characters, very common. And all this reversal of roles and interesting thing happens. So the question here we asked is that what makes a creative work successful? People usually talk about these 2 dimensions, right? What's the quality of the creative work versus what's the social influence? So how important are they? There was a famous music lab study that kind of shows that social influence play an important role in success of cultural products. But here our question is, like, what's the context? Can we look at creative work out of the context? Creative work obviously depends on all the previous literature and cultural products, and we need to think about those contexts. So if you are like me, you may choose the same like formulaic Marvel movies over the most critically acclaimed movie ever made when you sit down and try to watch a movie. And the thing is, like, it's very common that the same stories be played again and again. This is all the scenes where Batman's parents died. The deaths of his parents depicted in many different versions of the movies and stories. And if you look at 2018 and 19 movies, I think like 90% of them are either remake, reboot, sequel, or part of a universe like Marvel. So it's kind of crazy, mind-blowing that literally like so many, like every movie at the top is something that repeat something familiar to us. And you probably know this Kurt Vonnegut's Shape of Stories, right?
Now, this is an exercise in relativity, really. The shape of the curves are what matters and not their origins. So we'll start a little above average. Is why get a depressing person? We'll start. The whole thing we call this story Man in Hole, but it needn't be about a man, and it needn't be about somebody getting into a hole. But it's just a good way to remember it. Somebody gets into trouble, gets out of it again. People love that story. They never get sick of it.
Yeah, and Hero's Journey, of course. So there are these kind of really interesting pattern that repeat in the stories. But at the same time, there are innovations like that change kind of how things are made and how stories are told. So so people have been interested in this kind of novelty aspect, like what do we enjoy in terms of novelty and complexity. And one of the kind of famous kind of canonical theory behind this is something called Bund curve or Bund-Verlin curve. And it's like super simple. What it argues is that the hedonic value, how much we enjoy certain things, goes up as something become more novel, but then it goes down after that. Well, it makes sense, right? If it's too novel, you may reject. If it's too boring, you may reject, which makes a lot of sense. And people have been kind of studying that a lot. And it's ultimately the question about exploration versus exploitation. So would you exploit something familiar, something that you know you'll enjoy, versus you'll explore and venture out to get something new? And there may be optimal in that. And people look at it in terms of like words. Do you like this word or not? Music, films, ads, like all kinds of aspects. And they find similar things. Okay, there may be optimal novelty. Yeah. So why fan fiction to study this topic, right? And actually, fan fiction have a really nice properties. Like for instance, things like fan fictions are organized around canon and fandom. So if it's about Star Trek, pretty much every fan fiction use the characters and settings of the Star Trek. So in a way, it's like well-controlled kind of set of creative work where the variation is relatively minor in terms of like the setting of the stories. So that's one thing. And another thing is fanfiction tend to be free, accessible to everyone, and it's free from like marketing. Like fanfiction rarely kind of become like mainstream. And that means we can kind of ignore the effect of marketing. So it's a nice like coherent set of creative work that we can compare with each other. Yeah. And we use data set called Archive of Our Own. And this is a basically free online website where you can post your fanfiction and people read and comment and give likes or kudos and so on. So here's size of fandoms, like Marvel Comics has the largest fandom, and it has been growing a lot since like early 2000. And it's essentially works like this. You can navigate through fandoms. If you go to Marvel, you can sort and you can look at like hits, kudos, all these things. And there's a really interesting fan fiction called I Am Groot. And from the beginning till the end is I Am Groot. Yeah, you get the idea. So this is kind of fan fictions. And what we did is we estimated the novelty of a fan fiction using the past fan fiction in the same fandom. We use two methods. The first one is a term-based novelty, like basically TF-ID vector. It's again like embedding in a traditional way. So you calculate TF-ID vector of each word and use that to represent the document. And once you have TF-ID vectors, then you can calculate the average of the past. And then we can look at the focal fan fiction and measure the distance between the average of the past and the new fan fiction. And this is our novelty measure. And we can also do that with topic. You can do the same thing with the LDA, topic distribution space. You basically represent each document as a distribution across topics. And we can again measure the average of the past and measure the distance between the current fan fiction and the average of the past. And we did some stratified sampling and close reading of the fan fiction using these measures. And one of the most novel fan fiction was I Am Groot, which makes sense. And other one was something called Real Meaning of Idioms, which was posted on Sherlock Holmes fandom. And the entire fan fiction consists of text messages. So if you watched Sherlock, there are a lot of text messages going on, and it pushed that to the boundary. So everything is text message. So we found that the novelty measure kind of makes sense. Really high novelty tend to be like really innovative fan fictions. And then we measure the novelty, how novelty is correlated with the average success, which is measured in terms of like kudos, which is like button, and hits, and comments, and bookmarks. And if you look at term novelty, it actually doesn't really show this optimal pattern. It shows like decreasing patterns. So as it becomes more novel, it decreases, the success decrease. Interestingly, variance of success, like how variable the success is kind of showing interesting pattern. And what's most important is kudos, the black line. It kind of increased a little bit. It has a little bit of a peak, and then it has a high variance at the large novelty. So what it says is the more novel it is, it tends to not success, but there are kind of wild successes at the end. So very different from this Wundt curve. And we can look at the topic novelty, and it shows somewhat similar pattern. And this is comparing topic novelty and term novelty at the same time. And if you look at it, there tend to be more kudos around the origin, but at the same time, there are some spots with a really high novelty, high term novelty and high topic novelty. So that means there are some successes at the extreme. Yes?
Maybe you could tell a bit how to read this graph?
Yeah, so x-axis, horizontal axis is a term novelty, and Y is topping novelty. And then the color is the average success in terms of kudos in the left. So like green color means there's some like really successful fan fiction at that location.
Okay.
Yeah. Yeah, but this doesn't tell us much because there are so many other factors. Yes, Max?
So could you go back for a second? So basically the key take home is, in this particular case on the left, you cannot be novel, because otherwise, if you're novel, you're not successful. And you can be sort of successful if you have novel topics, but then the terms can't be new, or you have novel terms, but then the topics can't be new, in essence. Does that make sense? So you cannot, to translate that to multidisciplinarity, you should not innovate in both method and subject domain, in a sense. Is that?
Yeah, you can say that. Yeah, yeah.
That's sad.
but there are some success at the extreme, like high top novelty and high topping novelty. It's a unique island.
Everybody takes note. We need to be super outrageous, or like only conservative in one and then outrageous in the other.
Or be boring. Yeah, so but this doesn't tell like whole story because it doesn't control for other factors. So we did the regression analysis. I'll skip details, but we included all kinds of variables. And this is the result. And what it shows is a kind of the same thing, but in a more nuanced way. And I think this is an interesting part you can see. So first of all, it confirmed this negative trend. The higher the novelty is, you tend to suffer. But interesting thing is the square term has a positive coefficient. That means it has a decreasing trend overall, but at the same time, it has a kind of this concave shapes. What means is it may be U, not inverted U shape. It may be like totally different. And to really see that, we use the GAM method, generalized additive models. And what it does is it's a regression model, but it uses like any kind of continuous functions to estimate the shape of the dependence of one variable to the other. And the GAM result looks like this. So it indeed shows kind of somewhat U-shaped pattern. In other words, as novelty increases, you tend to suffer. But if you are really, really outrageously novel, people tend to appreciate that. And there's a higher variance in these high novelty areas. So either you spectacularly fail or can spectacularly succeed. So, so I think that's a kind of interesting implication. Yes, Max?
No. I didn't want to ask a question.
Yeah, so our interpretation is that readers may not actively seek novelty and just like what they used to like, just consume the same thing over and over again. But when they encounter something like really novel, they may appreciate. And some of the most kind of appreciated fan fictions, actually the most novel fan fiction ones. The fan fiction that got the largest number of kudos is actually the one I showed you earlier, I Am Groot. So it was the most popular fan fiction because of this kind of innovative novelty. Yeah. And also they tend to employ like crossovers, like remixes. That's another interesting thing. And this tells us like totally different like implication in terms of like how culture evolves. The optimal novelty theory tells us that it may evolve like gradually. Yeah, just keep changing little bit by innovating like small. But this U-shaped curve tells like the other story. In evolutionary theory, there is a kind of neutral evolution theory versus like punctuated evolution theory. Neutral evolution means you just keep drifting in the space, in the possible space, because most evolution doesn't make a lot of difference. But in the punctuated equilibrium theory, you stay the same for a long time until there is a huge jump. So depending on inverted U versus U, you may have a something of a kind of gradual evolution versus like kind of jumpy, punctuated evolution. But I would like to note there are many caveats. It's a very special population of authors and readers. And yeah, don't take it too seriously. Yeah, and Elise is the first author, and it was with Simon Didio. Yeah, and thanks.
Too many links to people who already spoke. No, I'm kidding.
Huh?
Too many links to people who already spoke. No, thank you very much. So this is sort of the second to last of a series, sort of. There is a number of people I invited. And so Peter Dodds spoke before, Simon Didio spoke before, and soon it will speak in 2 weeks. And the reason I did that was twofold. One is I wanted to sort of underscore my own background a little bit. So my own group or the group I'm working with actually gets an idea of like where my ideas come from, both in terms of like people I work with, but also people who, you know, Simon is quite interesting, right? So there was like, when we were at Barabasi Lab, there was like the other rivalry group was sort of Santa Fe Institute and surroundings. But now obviously we're one generation or two generations down. There is like much more overlap. And so the interesting thing is that, of course, you may say fan fiction is taken with a grain of salt, or has to be taken with a grain of salt. The community is small and so on. But nevertheless, you touched on all these issues which are super important in cultural evolution, cultural analytics, cultural dynamics in general, that go on a very long time. Art historians talk about similar issues since 150 years. Historians talk about issues like that, like, you know, our group member Mila Oiva talks about pseudo-history. It's very close related to that. And so I think there's a lot of interesting kind of ideas in there, and particularly this idea of punctuated equilibrium. One of the interesting things about cultural evolution is that you typically don't have these like nice little data series where there's lots of stuff, where you can do a nice time series. And, you know, you can work over centuries, have lots of data, and still find sort of these like punctual examples. So you cannot look for punctuated equilibrium if your data is only punctual in that sense, because you only got 5 sources over 500 years for a particular fact. So we have to take what we got, and we need to take a look, and yes, look at it with a grain of salt, but in the same way we should look at quote unquote serious history with a grain of salt, because there we get the same kind of issues going on. So we neatly filled 2 hours. I thank you very much for everything here, and I hope like there is many strings and ideas that come out of this, and catching up on methods, but also sort of coming up with ideas of potential collaboration. And so, as always, I would like to stay in contact, and what I would like to do like further down, because there's many other people that should speak and should be heard. I would like to do a kind of lab encounter thing. So we actually see what's going on around people like YY. And as you can see, I think this is a really big example this iSchool, Information Science School at Bloomington, is a really neat example for something that basically left disciplinarity behind. Yes, there are some common methods, but you can think about many, many different things. And the idea of using Word2Vec to look at mobility is something. It's really hard to have in a linguistics department. It's also really hard to have in a transportation planning department. But it's a no-brainer in an information science department. And if you, obviously 9 out of 10 times you find out what that doesn't work, but sometimes these things work, and do it strategically is sort of something that's really neat. And I thank you very much for giving these kind of examples.
Yeah, thanks for having me. Yeah.
Thank you. So with everybody else, we're now in full lockdown modus. So we talked about a novel way of communication after the meetings, which I assume is not today, but we will try to start next week. Next week, there will be a lab encounter with Digital Humanities Society in Estonia, which will be great. And again, a very diverse kind of set of things. And a week later, we will have Sune Lehmann from DTU Copenhagen, which again is a loop back to mobility, but in a different kind of way. Thank you very much. So see everybody.
Thanks. Bye.
Bye-bye.